next lecture, we will study about the impulse and the step signals. Before that, we will study about some typical the pulse shapes. The first one is a rectangular one. The rectangular pulse are defined like this way. If pi t are given like that, if t is minus 0.5 to the 0.5, then it becomes the 1. Otherwise, it is 0. So we can plot that one like this way. This is 1 and this is 0, minus 1.5 and minus 1.5. So signal patterns are given like this way, 0 and 1 and return back to the 0. So only between minus 1.5 to the 1.5 during this period is positive 1. All the other time is 0. This one is a rectangular pulse. So what about this one? In this case, the time is scaled by 1 of tau. So in this case, the pulse shapes looks like this one. Okay, 1 and back to 0. So this is 1, but in this case, this is 1 over tau over 2 and tau over 2. It's scaled by tau times because of this scaling. So we know that the time scaling factor, if we are 1.5 time scaling, then the time expansion is occurred 1. You know that by taking inverse of that one, we multiply that. This is the scaling factor. So pi t over tau looks like this one. This is time axis. Okay. The next one is a triangular signals. Triangular signals are expressed in this way. In this case, the signals are expressed like this way, like a triangular, although the time is 0. So this one is 0 time, and this is a 1. This one is minus 1, and this one is 1. So if t equals 0, then it's 1. If t equals 1, then it goes to the 0, back to like that. If t is minus 1, then this is 0 and all the way down to 0. You know that if minus 1 to the 0, it is a slope is 1, like that. And if t exists in between 0 to the 1, then it is slope is minus 1, and starting from the y-intercept at 1, so it follow this one. All the other cases is 0. Okay. This shows a triangular signals. I plotted them over here. So similarly, what if we plot this one, triangular t over tau? Then we need to consider time scale factor. So this time scale factor are given like this one. Time factor like this one. This is 0, scaled by minus tau over, it's tau, minus tau, you know, this is better. So this curve, but the intercept point, you know that minus 1 is scaled by tau, minus tau, and plus 1 scaled by tau, and magnitude is 1. So this is the curve. Okay, so in this case, this one 1 over tau times t plus 1. If minus tau t less than 0. Okay, these values are given like that. If t exists in between here, that's the t is greater than 0 and less than tau, then it follows this curve. So in this case, slope is minus 1 over tau, times t plus 1. So all the other case is 0. Otherwise it should be 0. So if t is less than minus tau, then it's 0. If t minus tau to the 0 in between here, then it follows this curve. Slope is 1 over tau, okay? And the y-intercept point is 1. And if time exists in between 0 to the tau, then it will follow this curve. So intercept point at the y-axis is 1, and slope is minus 1 over tau. This is slope, and this one is intercept point, and this is one shows that the domain range. Okay, this one is otherwise all values are 0. So we study about the two pulse shapes. One is the rectangular and the other one is a triangular. The last one is a sine function. Sine function is defined here. If t is positive, it's 1. Okay, this is 1. If t is less than 0, then it is minus 1. If t equals 0, you know that otherwise means this was t equals to 0. If t equals to 0, then this is 0. Okay, so sine function looks like this one. It's time is positive, then it is 1. If time is negative, then it becomes minus 1. And if t equals 0, then it's 0. Okay, so we think about the basic three functions. And next, I would like to explain about the unit impulse and step in discrete domain. In discrete time signal, delta function are defined like this way. If n equals 0, then it's 1. Other cases, all time is 0. So I can plot the unit impulse discrete signal like this way. This is index sequence n. If if n equals 0, then this is 1. Okay, this one. All the other case is 0. N equals 1, 2, 3, whatever, it's 0. Minus 1, minus 2, and whatever, it's 0. So only non-zero at n equals 0. Okay, this one is the unit impulse signal. This is definition for the unit impulse signal. The second one, unit step signal, is defined here. Un is 0 if n is less than 0. Other cases, it is 1. So I can plot the same curve here. This is index n. If n equals 0, then this is 1. And positive index is 1. Okay, 1, 2, 3, whatever, all they are 1. But in less than 0, minus 1 is 0, minus 2 is 0, like that. All the other negative integer index is 0. So 0, 0, 0, and at this point this is 1 and remain in the positive 1. So we talk about the unit impulse signal and unit step signals, and here shows that the relationship between the unit step sequence and unit impulse sequence. You know what? That the unit impulse sequence can be defined like unit step sequence n un minus u to the n minus 1. Okay. If n equals to the 0, then delta n are u0 minus u to the minus 1. u0 is this point, 1. But u minus 1 is 0. So this is 1 and 0, this is 1. What about the other n? 1, 1 or 0, 0. So 1 minus 1 should be 0, and 0 minus 0 also 0. So all the other cases is 0. So this satisfied this delta conditions. So unit step, by taking difference in the unit step, n and n minus 1 will give the delta n. So this shows that the relationship between the unit step and unit impulse. This one is unit impulse. and un, this one is a unit step. What about the other cases? You know that m can taking minus infinity to the n, and for example, okay, yep. Delta m equals u m minus u m minus 1. Okay, delta m plus 1 equals u m plus 1 minus u m, and delta m minus 1 equals u m minus 1 minus u m minus 2, like that. And we do this one, goes on, and stopped at delta n. Then this one is un minus un minus 1. So we would like to adding all these numbers. Then we summing from minus infinity to the n. So we minus infinity to the, oh, this is typo, this should be n. Then by adding that one, you can see this one is cancelled out. This one also cancelled out, like that. Cancel out. Only un is remain. It says that the un should be equal sum delta m from m equal minus infinity to the n. M equal minus infinity to the n. By summing up, we can find out delta n because of these cancellations. Okay. So at here we talk about what is the unit impulse sequence in discrete domain and what is the unit step, and also the relationship between the unit impulse and the unit step in two different point of view. One is the delta n, the other one is the u to the n. So keep in mind that this is typo. So minus infinity to the n, by adding that one, by this process, the sum of this one should be equals to the u to the n. Okay, so we talk about in discrete domain what is the unit impulse and the unit step. The same thing can be think about in the continuous domain. In continuous domain, unit impulse and unit steps are defined here. Here is a unit step. Unit step is looks like this one. If t is less than 0, it's 0. But t is greater than 0, then this should be 1. This one is defined as unit step function. The problem of this unit step function is this continuous at t equals 0. It's a step change. Okay. If we taking derivative with respect to time for the unit step function, it is defined as delta functions, impulse function. The inverse of the differentiation is integration. So by taking integration of delta function with respect to time minus infinity to t, okay, here is some ambiguity, so I'd like to correct these equations. Okay, ut should be expressed in this way, into t. Okay, a should be minus infinity, and delta tau we have to integrate in this way. So I would like to correct these equations like this way. So by taking integration of time derivative, it means that the du tau of d tau is a time derivative. Okay, that becomes the delta function. Then we taking integration of this one, we can have a unit step. The delta function looks like this one. Delta function is defined as 0 if t is not equals to 0, and infinity at t equals 0. But this is not enough to describe the delta functions. The requirement is this one: minus infinity to the infinity delta t, summation should be equals to 1. And the same thing is this one. Unit step function should be delta tau d tau. So by integrating delta function, it should be unit step. You can compare to the discrete versions. In the discrete version, the delta sequence equals the difference of the unit step sequence. But in the continuous domain, the differentiation of a unit step function with respect to the time equals to delta function. This one are similar to these equations. Okay, in discrete version, unit step sequence also defined by summation of delta sequence. And in the continuous domain, delta function should be integrated over time. Then it gives a unit step. So you can think about that. The difference is in the sequence domain, we're taking summation of the impulse. But in the continuous domain, we just take integration of that. Okay, so we talk about the discrete impulse and unit step, and also continuous unit step and impulse. In the discrete domain, impulse and unit step is quite easy to understand because it is clear to look at here that the value is specific. But in the continuous domain, there is some ambiguity because of the impulse function has infinite value at t equals 0. If t is not equal to 0, it is 0. And unit step has some infinity slopes at the t equals 0. It means that there is discontinuous at the t equals 0 times. So we can make it reasonable approximation of that one. So then it means that some unit step has some finite slopes and t. Then we can define this one in this figure. We can define that function in this way. Okay, this is t equals 0. If t is less than t equals 0, u delta t is 0. And after some finite delta t, it should be remain 1. In between, there is some finite slopes exist. Okay, this one 1. So this function is defined as u delta t. U delta t looks like this one. If 0, if t is less than 0, this is 0. That's it, this part. And if t is greater than 0 and less than delta, okay, in between here. So t equals 0 to the delta. Okay, this one is delta. Then slope is 1 over delta. Okay, t. Okay, this is it. So slope is 1 over delta. It's time change the delta, but the actual voltage change 1. So the slope is 1 over delta times t. And if t is equality here, greater than equal to delta, then it should be 1. Okay. So this is definition for the u delta t. You can think about the approximation of this unit step can be expressed like that way. This one is a approximation of that. And then what about this one, u delta t of t? Then this becomes the delta t, approximation of impulse functions. You can think about it by taking differentiation. This part is equals to 0, but this part, okay, this is time t axis. Okay, this is time t axis. This is t equals 0. So I would like to plot the u delta t. So by taking derivative with respect to time, in this range, you know that t is less than 0, the differentiation is 0. But if t in between 0 and delta, the slope is 1 over delta. Okay, it remains in this way, 1 over delta. And after that, slope is 0 again. So this is the delta t, okay, approximation of the ideal impulse functions. This can be described like this way. If t equals to t in between 0 and delta, then this is 1 over delta. In the other case is 0. Otherwise 0. If t exists in between 0 and delta, then it has this value. That's this slopes. You can think about, obviously, this area equals to 1. So you can delta times 1 over delta gives 1. Can be expressed like this way: minus infinity to the infinity delta t over dt should be satisfy these conditions. Okay, that's this one. This condition are satisfied here. Okay, so we talk about discrete time impulse signal and step signal and their relationships. The relationships says that the delta sequence are difference of a step sequence, and by summing the delta sequence up to n, it gives a un. And similarly, in continuous domain, even though the ideal impulse and the unit steps are ambiguous at t equals 0, means that in the t equals 0, continuous unit step is a step change at t equals 0. It's an infinite slopes at t equals 0. Due to that one, the impulse response has an infinite value at t equals 0. But satisfied the same conditions of this one by taking integration of delta function over whole time domain, it should be 1. And the time derivative of unit step should be equals to delta t. So that's that shows the similarity relationship between impulse discrete domain and the unit step relationship between impulse and the unit step sequence and function. To approximate the ideal unit step function, I introduced the u delta t. The difference between ideal and approximate one is this one. In case of ideal, it follows this curve. But in the approximate one, we allowed some finite slope. And to allow that one, we have some finite time duration of delta t, delta. During this time, the step changed, 0 to the 1, increasing like that. So the slope is 1 over delta. Then approximate version of unit step can be defined like this way. If t is less than 0, it should be 0, but in between 0 to the delta, it should have some finite slope. The slope is 1 over delta, this one. And if t is greater than delta, it remains as 1. So approximate the ideal unit step like this way. And by taking derivative with respective time like that, then we can get the approximate version of delta functions. That delta function are defined like this way. If t exists in between this range, then the slope is 1 over delta. Other cases, this slope is 0. This is also slope is 0 by taking derivative with respect to time. Both 0 and 1 are constant. That's why it should be 0. So this one says that the approximate delta functions and is satisfied the integral conditions by taking integration over time equals to 1. Okay, we talk about the delta and the unit step function. These two functions are very important to characterize systems. I would like to explain why delta function is so special. It's related to sampling. Okay, here shows a input signal xt. Okay, xt is here, and delta function, approximate delta function are shown here. This delta function are 0 all the other times except t between 0 and delta. If t exists in between 0 and delta, it has value 1 over delta. So that's the definition of this delta function. To sample that one, we can multiply sampling function and input signals. So xt is multiplied by delta t. You can see here that by multiplying x1t looks like this one. Only this part is changing, but delta is very small period of time. Then we can approximate the one like that. Okay, even though these x1t are changing over this delta during this delta time, but it can be approximated as this value. So we can approximate in this way, and if we take delta as a limit to the 0, then okay, this one is almost looks like the ideal delta function. You know that approximate version of delta function, if we take delta as a 0, then this should be ideal delta functions. Okay, if we reduce this time period of delta smaller and smaller, then it follows this curve, and we can replace the xt with x0, because you know that all the other time except t equals 0, all the time is 0. So this is the same as this one. So this is sampling function. We sampled at t equals 0 value. So we can think about here, if we shifting the delta functions, time shifting like this way, we shifted time t0 and multiplication. It means that we shifted this value at t0, but sampled another times. In this case, we can think about this one, minus t0. Okay. Here it says that xt is multiplied by shifted version of delta function. Then we can replace the xt with the xt to t0 like that, similar to this one. Okay, we can replace that one. Then look at here, xt is multiplied by delta functions. Then we can, this equation can be rewritten like this way, minus infinity to the infinity. Xt can be replaced by xt0 and multiply delta t minus t0 over dt equals to, now you know that this is constant with respect to time. It doesn't change over time. So we can replace that one into this way, t0 dt. But you know what? The delta function definition, this should be 1. That's why we call this one is looks like the one. So you need to think about by the integration of delta function is quite easy. So if there is any delta function like this one, delta t minus t0 times xt, by taking integration over time, this always should be this one. This is sampling value at t equals 0. So this one can working as a sampling function. When we calculating system response, this technique widely used. Okay, so we talk about the several the pulse shapes and the unit step and impulse functions. You know what that okay,